Hello, good evening everyone. Magandang gabi sa inyong lahat. I am John Lim Hap and I lead the Philippine .NET Users Group, and this is our April edition of the PHINUG online dev sessions. All right, and tonight we have a very special guest. So let me just give a little bit of history. When the pandemic came on, PHINUG was not prepared to take on the new format of going on to a live stream and going on to shifting from live events to online events. And 2020 basically went on with just one or two joint events with other Microsoft user groups in the Philippines. But towards the end of the year, someone contacted me from Microsoft, and he's a friend of mine, and he said, "Oh, aren't you going to make a .NET Con for 2020 or even 2021?" And I said, all right, if you could help me set it up, and we could make it happen. Let's make it happen. So after a few months, come January 2021, that's our very first PHINUG live streamed event. And if not for this person that we're going to speak to tonight, that wouldn't have happened. So before I introduce you to our uh, speaker, I still wanted to try to pronounce his name correctly, Laurent. I don't know if that's right, Laurent Bugnion. Let me first thank our other sponsors, other people who help us with this event. First of all, my employer, Page Up, which is supporting me in doing this live stream. Yeah, supporting me in a way where I actually might have a support case right now, but yeah, I'm here hosting this event. And yes, the .NET Foundation, which we would like to thank for making this stream possible. We're streaming live online on their YouTube channel, so please subscribe, like and subscribe the .NET Foundation YouTube channel. And yeah, if you want to also look at other .NET um, user groups around the world, which the .NET Foundation supports and helps with not just events online, but also providing them with materials for presentations and then linking them to resource persons. Please, yeah. Please follow their meetup.com or join their meetup.com. That's .NET dash virtual that user dash group, so that you would see different .NET user group events around the world. All right. And yep, if you still haven't followed us on any of our social media channels, please follow us on Twitter, join our Facebook group, and our meetup.com, of course, and the LinkedIn. Please look us up there, and join us. All right. Um, so I'm good. So yeah. So as I said, um, all right. I'm going to say the easier way to pronounce it, Laurent. I met him. I think 8 years ago in Redmond in one of the MVP summits, and yep, he's a really great. He was an MVP before, then he became regional director, and now he's a senior advocate for Microsoft, and he will be with us tonight to talk about deep learning. And yeah, so please join me in welcoming Laurent Bugnion.
Well, hello, John.
Hello.
Hello, everyone.
Hello.
I want to say, magandang gabi and mabuhay. Hopefully, I don't butcher the pronunciation. Even after a long time being married to a Filipina lady, my Tagalog is still very bad. So
that
we'll speak to each other.
that is absolutely fine. So you were here recently, right? You
Indeed.
visit you visited both volcanoes.
Yeah,
Both
yeah, indeed. I went
volcano,
from
the
the
bigger
most
volcanoes of
active
Luzon.
volcano in the Philippines to the first most active volcano in the Philippines. So there is a trend to that. No, we got really hit by the pandemic, couldn't travel for a long time. My wife, like I said, is Filipina. Her family is based in Alfonso Cavite. And we couldn't see them for a very long time. And we got married last year and couldn't celebrate with friends. So as soon as the Philippines opened up the quarantine, we decided to come. And I was lucky to be able to work from the Philippines. So I worked there for 6 weeks, including a lot of travel. And we were hoping to do this event in person
Yeah,
in the
that's
Microsoft Office and couldn't because of the current restrictions. So next best thing is doing it online. But definitely next time I'm coming, we'll meet in person as
yeah.
well.
We'll make a hybrid event. We'll have
All
some
right.
people in person. And anyway, let's move on to your talk and let's find out what deep learning is because I don't have any idea about what it is.
All right. No, absolutely, absolutely. I'm very happy to do so. So again, welcome to everyone. Like John said, my name is Laurent Bugnion. I work for Microsoft, and I'm a developer. I'm not an expert in what I'm going to talk about, which shouldn't surprise you because usually this is what people do, right? They talk about stuff that they don't necessarily know. Nonetheless, I was very interested into AI, deep learning, and machine learning. And I went to some of the best people like Cesc Juarez, one of my good friends, who's also working for Microsoft, who he is a data scientist and he really understands this stuff. And I told him, look, I really would like to understand. I went to some of his presentations as well, and he really helped me to understand some of the concepts. And another breakthrough moment for me was finding a course. I'm going to link to that at the end of the presentation. It's an MIT course, which was talking about deep learning. And I went through it. I'm not going to pretend that I understood every detail, every aspect of it. Nonetheless, it really helped me to understand, and especially to understand that some of the math that I had learned, mathematics that I have learned as an engineer back then in school, and that was a long time ago, that was like probably 25 or 30 years ago, is applicable here. And so that was really interesting. So when we talk about AI and machine learning, deep learning, we have some images from the movies very often. This is one that you might know if you're as old as me. It's, of course, War Games. It's a great movie. It's one of the first movies that I remember personally watching as a kid, or probably I was a teenager, I guess, where you had a machine which was able to think. And one characteristic of that is that the machine wanted to kill everyone, right? Because it didn't understand that it was actually playing a game, but that game was actually reality. So that was quite scary. If we go even further back in time, 2001: Space Odyssey with HAL. HAL, whose name comes from IBM, so they took the letters after I or before I, B, and M to do HAL. Now this is a very old movie, right? It was filmed even before men went to the moon, right? And so you have to imagine that at the time it was really a revolution to see on the screen a computer able not just to talk, able to understand, but also able to think. And one interesting trait of that movie is that the computer wanted to kill the crew because it had some moral conflict about what it was supposed to do. And then, of course, we have the Terminator, and here there is no moral conflict at all. It just wants to kill everyone. So what is the common denominator of those movies? Of course, the AI is bad. And there is a little bit this impression that we have that AI is bad for us. It has also to do with ethical issues. We'll talk about that a little bit at the end of the presentation. But this is interesting to keep in mind that our image of AI is flawed because of the movies. And of course, a bad robot is much more interesting than a good robot, I guess. In fact, we can even ask ourselves, does AI really exist? Does it even make sense? And marketing takes AI very often to the limits, right? So what is this device? This is a rice cooker. It's an actual picture I took in an actual kitchen. And I had to laugh because to cook rice, apparently you need AI. And I'm really wondering, why do you need AI to cook rice? And the answer is very simple. You don't, right? And in fact, I'm ready to bet that there is no AI in this machine. What there is, maybe some algorithms, some simple software which is going to detect, the degree of moisture of the rice, or whatever. But I can guarantee you, this is not AI, right? So it's just a marketing ploy to make people believe that they are buying something which is very fancy. So that made me laugh a little bit. So let's manage expectations a little bit. I have 60 minutes to talk to you, more or less. I have 52 slides, so it's going to go relatively fast. I'm going to do my best to answer questions. I also want to manage expectations for the questions. I'm not a data scientist, so I'm talking here about a topic that I kind of understand, but not totally. I'm going to do my best to answer your questions, but potentially sometimes I'm going to be honest with you and say, I don't know, right? I prefer being honest rather than, pretending to know something. So let's define a few terms and let's talk about the differences and some of the concepts and words that we hear, especially, deep learning, machine learning, artificial intelligence. What is that even? So intelligence is defined as the ability that people have, or beings, I should say, have to learn from their experience and to apply that experience and the acquired knowledge to repeat and to gain some benefits. All right, so you learn something and then you remember that you learned that, and then you're going to apply that to future experiences. So when I say beings, animals are able to do that as well, right? So you have some well-known cases of animals who use intelligence to basically progress and to gain advantages and comfort, etc. And then you have artificial intelligence, and artificial intelligence is basically that applied to machines. So some people will build some algorithms and develop some technology to help machines to do that, to acquire some knowledge and to apply this knowledge to future experience. And then you have machine learning, which is a subset of artificial intelligence, where we focus on basically building and teaching algorithms to take some information, and the machine should be able to learn from that process without being explicitly told what to do. So we don't, when we build an algorithm in programming, typically we tell the machine a sequence of rules. And here we don't tell the machine explicitly the sequence of rules, but the machine should be able to understand that, for example, based on patterns in the data that we use for the training. And then you have deep learning, which again is a subset of machine learning, which is like machine learning, but except that instead of really providing the data and teaching the machine explicitly, we are going to provide some raw data, and then we are going to let the machine have this experience by itself, okay? So it's a little bit the definition of those terms, if you want. So deep learning is a subset of machine learning, which is a subset of artificial intelligence. Now, when we are, I don't know if you are developers, I'm a developer, so I often come to a problem with a developer mindset. When I think about programming, what programming does is that it's going to take an algorithm, and usually we do that by reading books, by going on Stack Overflow, by checking existing code on GitHub, etc. And then we are going to translate this algorithm in code using whatever programming language, framework you like. Personally, I'm more of a .NET person. And then we are going to feed some data into the algorithm, and then we are going to get some answers based on the data and based on the flow that we program. But when we go to machine learning, things are different. And in fact, in machine learning, we are going to switch things around, and we are going to take answers being known state for an object that we want to analyze. We're going to feed some data, which we call training data, into the system. And then we are going to use a framework, for example, TensorFlow, PyTorch, etc., to create an algorithm. And this algorithm in machine learning, we call that a model. And the model is then going to go into additional code. And into this code, we are going to feed the actual data that we want to analyze. So the first set of data was what we call training data and validation data. And then we have really the new data coming from the field. And then we are going to get not answers, but what we call predictions. Predictions are different than answers because predictions are never absolutely exact. They are going to be on a scale of 0 to 100. I think that this is the probability for this to be correct is maybe 85% or 90%, etc. So we don't really get absolute answers here. So that is a little bit the difference in the workflow between machine learning and programming. Now, another thing which is really interesting that we can ask ourselves is machine learning and those concepts of artificial intelligence are actually very old. If we go back in time, we notice that the Neuron model, which I'm going to introduce a little bit later, was developed already in 1943. This is 80 years ago, if you can believe that. And the first AI conference was held in 1955. 1955 means that men had not been to the moon yet. So the computers were extremely primitive back then, and yet people were already thinking about those problems. And then there was a long lull where basically AI was more of a science fiction story. And why now is it really booming? Well, there are a few reasons. First of all, we finally have the amount of data necessary to actually go and train our models. And we need huge amounts of data to train models. So now we have the possibility not only to acquire this data, you know that everything is connected these days, everything collects data, but also to store the data in ways which are reasonable from a price aspect. For example, Azure storage, etc. We have big data solutions there that you can actually manage that, okay? Now, another thing is GPUs, and we'll understand in a moment why GPUs are important in machine learning. GPUs, of course, nowadays you have a little bit of a shortage because some people use that for Bitcoin mining, etc. It's not great for the environment and everything. But GPUs also have the ability to calculate in parallel, heavily parallel processing. We'll talk about that when we talk about linear algebra. And that's why they are very useful to basically increase the capacity of computing that we need to create models. And finally, advances in software, of course. Now we have very good libraries, for example, in Python or in other programming language, allowing you to basically train your models and do what you need there. So all those advances create a situation where now, and starting only maybe 10 years ago maximum, we have the possibility to actually apply those things that were developed, those theories that were developed long ago, up to 80 years ago. So let's talk about neuron and neural network. What are those concepts? So before we go into that, I'd like to do a few mathematical reminders, and don't be afraid. It's simple math, and I'm going to take my time to go through that. So let's imagine a situation where we have a number of inputs. And because we don't know how many inputs we have, we talk about x1, x2, xn, n being really any number of inputs in a system. And then let's imagine that we decide, for some reason, which we will understand later, we decide to multiply x1 by a number which we call w1. W stands for weight, all right? Don't be hung on terms and definitions. Essentially, we say we want to multiply x1 by a number w1. And then we want to multiply x2 by a number w2 and xn by a number wn. And then we decide that we want to take these products and we want to add them together, and then we'll have an output, okay? So this system can be expressed mathematically by a formula, and the formula is going to be, this is a sum, sigma, okay, for the sum of 1 to n, and that reminds us of as a developer of a for loop, right? For index equals 1 to n, of x with the index. So for example, x1 times w1, x2 times w2, x3 times w3 until n, and then we sum that up. So that's a mathematical expression for a sum of products. Okay. Now let's imagine that we want to do, say, to make things just slightly more complicated, and we say, well, okay, when we multiply an input, which can be anything, by a weight, which can be anything, we can get literally anything as a result. So the output, y, can be anywhere between minus infinite and plus infinite. It's not very convenient. So sometimes what we want to do is say we are going to normalize that between, for example, 0 and 1, between 0 and 1%. And to do that, we feed the output of the sum of products through a nonlinear function, which is going to transform that into something which we can then compare to other systems. For example, anywhere between 0 and 1, or anywhere between -1 and 1, for example, depending on the problem. And this nonlinear function, data scientists call that an activation function. You will notice that just like software developers love to use words that nobody else understands, data scientists also love to use words that nobody else understands. And so I'm going to try to define those as we go. So activation function is basically a nonlinear function, which is going to normalize the output between a certain range that you define. So if we add that to our formula, we had the sum of products before, and now we are going to feed that into a function. And this function is a nonlinear function. Depending on the problem, you can use different nonlinear functions. It depends a little bit. Then finally, the last thing we want to do is add some bias. And here we are not talking about the bias that you hear about when you talk about artificial intelligence sometimes, for example, racial bias or gender bias. Here we are talking about just a pure definition which says we are going to add a little bit like a button that you can turn to fine-tune the output of the output of this system, if you want. And so this bias, B, is going to be, again, a number, an arbitrary number, which is going to be later found by the computer when the model is trained. And we'll understand later how those W's and how those B's are calculated or are found, if you want. So if we add the B or the bias into our formula, this is actually a neuron. This is a model, mathematical model of a neuron, if you want. And sometimes data scientists talk about perceptron because, again, they love to use words that nobody else understands, just like we do as software developers. And if we add that into the formula, this is the mathematical formula corresponding to a neuron. Okay. So moving on, we are going to talk a little bit about linear algebra. And why do we want to talk about linear algebra? It's because you have to understand that when you do a sum of products like that, you're going to do it in our mind. We do it in a linear manner. We are going to start with x1 times w1, then we are going to add x2 times w2, then we are going to add x3 times w3. And just like a for loop in a program, which is processed in a serial manner, this is very slow. On the other hand, the computers have the possibility to work in parallel. And this is where linear algebra is going to become very, very useful. So let's remind us a little bit about linear algebra and some things that we learned at school. This is a vector with 2 dimensions. It has an x and a y. And this is fairly easy to understand. You can draw that on a piece of paper. All right, the vector is going to have a direction or an angle, if you want, and it's going to have a length. And this is basically the result. So you can draw that on paper. It's very easy. But of course, there are also more complex vectors. For example, with 3 dimensions. 3 dimensions is a little bit more difficult to understand. You're going to have a component of the vector which is coming out of the screen and pointing at you. Okay. So, but 3 dimensions, we can still grasp it because we live in a 3D world. And so we understand what it means. But maybe you have 4 dimensions and suddenly it becomes much harder to understand what it means. And potentially you even have n dimensions to a vector like that. Now, the good thing is that for us, n dimensions are almost impossible to understand or to represent in our mind. But for a computer, it doesn't matter. If you have 2 dimensions or n dimension, computers work exactly the same. It's just going to take a little bit longer to process. Okay. So when we work with vectors like that, it is allowing us to do some mathematical operations faster. For example, the dot product of two vectors, it's basically when you multiply two vectors, if you want, what you're going to have, the mathematical expression for that is the first line plus the second line. So the product of the first dimension plus the products of the second dimension. And that's how you transform basically two vectors into a scalar number, which of course computers know how to do very well. And most importantly, for computers, especially for graphical processing units, this is where we go back to the GPUs, they do that all the time, because when graphical processing units work, what they do is that they take an array of numbers, which are pixels on the screen, and then they are going to multiply them by another array of numbers, which is a filter you want to apply, and then it's going to do some operations on those pixels. And of course, GPUs are optimized to do that as fast as possible. And they process the dot product here for a GPU is just one simple operation, while for us, we need to do this in a serial manner, and so it takes longer. So that's why GPUs are very well suited when you have anything to do with linear algebra, including machine learning, and we'll understand that a little bit better in just a second. So this is a dot product. This is a dot product with two arbitrary inputs and then some weights. And now we kind of see the report with what we had before, right? With this sum of products with weights. And then this is a dot product with n inputs that you can represent as this sum of product here that we have, just the same formula that we had before. So when you have a number with n, a number of input n, and then you want to multiply that by a number of weights n, then you can express that by the sum of products, or you can just use the dot product in linear algebra, with the advantage that the dot product is going to be much faster to process. For a GPU, it's just one operation. Okay, so if we replace that in our formula, that's what it becomes, and that is something that computers are very efficient at calculating. So let's go back to our neuron or our perceptron, and we're going to simplify the notation a little bit to make it easier to understand. So first of all, we are going to just imply the bias and the weight. So I'm removing them from the notation. They are still there, but I just don't draw them anymore because otherwise it becomes too complicated. And I also remove the activation function from the diagram just to make it simpler to understand, but assume that there is an activation function. Now, one thing that we could do is say, all right, instead of calculating one simple input, I would like to have multiple outputs. And here I'm going to add another series of weights, and I'm going to sum that, and I'm going to add another activation function, and then I'm going to get two outputs, okay? Or we could even go even further than that, and we could say, well, now I want to have even more W's and B's, even more weights and bias, and we are going to end up with what we call these hidden layers. So those Z in the model, this is something that is inside our model. Our model is a black box. We can measure the inputs, we can measure the outputs, but we don't measure what is inside. And again, keep in mind that you have a lot of factors here of parameters, those W's, those B's, as well as the activation function, normalizing the output. Those, we are going to talk about them later and understand how the computer actually calculates them, if you want to compute them, to get the best possible result. Now, one thing that we could even do is say, well, now I have one hidden layer. So this is a notation where I simplify things. Why don't I add some layers? And here I have an example where, for example, I put additional hidden layers in the beginning. And of course, there is a certain amount of layers that you can add. This is going to increase the processing time. It's also going to potentially increase the accuracy of the output. So when you expect a certain output, you're going to fine-tune those W's and those B's so that you get the output that you are expecting. All right, we'll understand again how the computer is doing that later. But there is a certain amount of layers that you cannot exceed because it would take too much processing power to actually calculate everything, and the result would not be much better. So you don't increase your result, the quality of your result much, but you increase the processing power. So there is if you want, there is a point in time where you say, all right, now I have enough layers that my system is good enough. And this is a deep neural network. This is a network of neurons where you have multiple layers of those neurons interconnected with each other. Now let's talk a little bit about the activation function. This is this normalizing function, this nonlinear function, which is helping us to normalize the output. So one example of a function like that is, for example, the sigmoid function. This is a mathematical expression that we have here on the left. And if you plot that, for example, in Excel, which is what I did for this graph, this is the output, okay? And as you see, what it's going to do, it's going to say, all right, for very small number, very negative number and very high positive number, is just going to normalize everything to 0 and 1. And then for the numbers in between, it's going to basically have this ramp, which can be more or less steep, depending on what factors you use in the activation function. And that's going to basically normalize everything between 0 and 1, between 0% and 100%. Another activation function, which is very popular, was actually found a little bit by trial and error, and data scientists do that. They add some parameters to their system, and then they see if it works better or worse. And then essentially at some point they agree that, okay, there are some of those activation functions which work really well. And one of those is what is called a rectified linear unit, or ReLU. And you will see ReLU quite a bit, also a little bit further in this presentation. But also if you open a model with a model visualizer that you can get, for example, an Onyx model, which is a standard type of model, then you will see those ReLU quite a bit. And so this is how a ReLU looks like. Again, it can be more or less steep, it can be moved a little bit depending on the parameter, but basically what it does is that it normalizes the output between 0 and x. So it is basically ignoring all the negative values and taking only the positive values. So those are normalizing functions that data scientists use sometimes to kind of activate the result, or to basically to normalize the result between certain values. Good, so let's talk about an example, and hopefully that will help you to understand a little bit better all those concepts and all those words. So we are going to try to solve a problem. This is called the 9-square problem. What we want to do here, we are going to have 9 squares with random values of gray. And those values of gray are going to be between 0 and 255. And we're going to decide, for the sake of the problem here, that 0 is white and 255 is black. And I know that normally in graphic computer, this is the opposite. 255 is white and 0 is black. But it's easy to turn, and it makes my life easier if we go with 0 is white and 255 is black. So let's decide that. So here we have this square. We have the first one is 182. It's kind of a medium gray if you want. The next one is a little bit darker, so 199. The next one is lighter at 90. The next one is almost the same as the previous one at 100. The next one is almost the same as the one right above at 200. 199, 200 is almost the same. Then we have almost 255, so almost dark. And then we have here in the bottom right corner, we have 4, which is almost 0, so it's almost white. Now, the problem we want to solve is we want to find out if the top row is darker than the bottom row. And we don't care about the medium row. We just want to know if the top row is darker than the bottom row. And of course, here, immediately we know that, yeah, obviously the top row is darker, right? It's easy to see just with our eyes. But of course, if you have a lot of those problems to solve, you probably want to optimize that a little bit and probably want to use a machine to do that, okay? So how are we going to do that? Well, let's apply what we learned before. We are going to say, all right, we have 9 square, we have 9 inputs, x1 to x9. And then I'm going to use some weights, w1 to w9. I'm going to multiply the input by the weight. And then I'm going to add the result. And then, because I want my output to be easy to read, I'm going to say I want the result to be between 1 and -1. And I want the result to be either 1 if the top row is darker, or -1 if the bottom row is darker. All right, that's the output, and this is what the activation function here is going to do. So it's a custom activation function that I write for this exact purpose. So how do we find out the W's? How do we find out the weights here? Well, first of all, we can reason a little bit. I told you that the middle row, we don't care about it. So it means that I can probably say, here are, by the way, the numbers that I feed, the number from the same, from the first square that I feed into the system. So we can say that the W4, 5, and 6, which correspond to the middle row, I'm going to set them to 0 because basically they don't influence the system at all. So I'm just setting them to 0. And then one way to determine if the first row is darker is to sum up the number of corresponding to the grades of the first row. And then I'm going to sum up the numbers corresponding to the bottom row. And I'm going to compare them. And if the top row is darker, the number is going to be higher than the bottom row. So one way to do that using those W's is to say the top row I'm going to multiply by +1. The bottom row I'm going to multiply by -1. And then I'm going to sum everything together. So here in that case, the top row amounts to 495. The bottom row amounts to 259. This is smaller than 495. It means that the top row is darker. So I just change the sign to add them together, and then the result is going to be positive. It's a positive number. If I feed that through my activation function, it's going to just take the sign, and the sign here in that case is plus. It's +1. If I had the opposite situation, the result would be negative. After passing through my activation function, I would have -1. Okay? So now I have basically used my brain to come up with values for those W's which make sense. Now, this is something that humans can do, but computers cannot do. Computers cannot use their brain to think about a problem and find a rational answer, okay? What they can do, on the other hand, they can try very, very often because they are very fast, and then they can find out what combination of W's are the best values for the values that they want to have. All right. So before we understand a little bit how it goes, let's define a few numbers. Let's define a few terms, sorry. And we are going to talk about supervised learning versus unsupervised learning. So here in the examples that we are going to show and continuing this presentation, I'm going to talk about supervised learning. Supervised learning means that I'm going to give the computer some examples which I classify, which I label. For example, I'm going to tell, okay, so this is a set of pictures that are all of pizzas. And then this is another set of pictures, which is all from hot dogs. And I'm going to give that to the computer, and then the computer is going to learn from that. So this is supervised learning. This is very good for things like image classification, when you need to get an image and to understand, is it rather a pizza or rather a hot dog? Okay. And then after that, you have unsupervised learning, where you feed some data to the computer and you let the computer learn from the data, but without explicitly training the computer. And for example, the computers are going to do that by analyzing clusters of the data. So they are going to detect some patterns in the data, if you want. And this is good, for example, for image recognition, when you have you feed the data, which is the number of pixels, and then the computer is going to find out where you have clusters of pixels and be able to say, oh, this looks like eyes and nose and mouth. This is probably a face. And then it's going to draw a square around it. This is what every camera does these days, right? Then you also have another classification of learning, which is reinforcement learning. And reinforcement learning is basically what you do very often with a pet when you want to train a pet, where you teach by giving rewards for good behavior, for good learning. And we can do the same with the computer and give a reward to the computer when the computer is learning well. So basically by praising, if you want. So again, in the follow-up of this presentation, in the continuation of this presentation, we are going to talk more about supervised learning. Good, so understanding that, we still need a little bit maths. So bear with me, we are going to talk about derivative functions, because we are going to have to calculate the slope of a model, of a system, at a given point. And you're going to understand later why we need that. So here is a simple function, all right? It has x and y. This is actually the square value of x that I represent here. It's a parabolic function. And let's imagine that we want to draw a line through 2 points. I can calculate the slope of this line simply by doing here delta y divided by delta x. So basically the difference in vertical value divided by the difference in horizontal value. That's the mathematical definition of the slope of a line. Now, this line can be anywhere on my system. It doesn't really tell me much about my parabolic function. But imagine that if I want the slope at one given point of the function, not at 2 points like now, but at one given point, I can simply reduce the value of delta x until it is 0. And then I have only 1 point. Okay, so I have this, and then I do whoops like that. So what we are going to do, we are going to let delta x tend to 0. All right, and if we do that, this is what happens. It becomes very, very small. It becomes always smaller until dx is 0, and then we have just 1 point, and then we know the slope of this parabolic function at this given point. And for us, we know, because we learned this in engineering school or in high school for some of you, that we know that the derivative function of x squared is 2x. So the slope at any given point is going to be equal to 2 times the value of x. Okay. Now we know that because we learned that by heart. Computers can do that, but computers are actually very good at calculating the derivative of a curve. And they do that the math teachers are laughing at me as well. Believe me, that was 30 years ago, right? So now you finally understand why they push derivative functions on you. It's because we use that in deep learning, right? So why do we need that? It's because we are going to try to do something which is called error reduction. So remember, this is supervised learning. So we're going to give some data to the computer, and we're going to give also the answers to the computer. For example, we give a set of pictures, and we say, all right, those pictures are pizza, those pictures are a hot dog. And the computer is going to try to use this data, in this case, the pixels, running it through those W's and B's until it gets as close to, yes, this is a pizza, yes, this is a hot dog. And of course, there is going to be some error, especially in the beginning. He's going to get it wrong. They are going to get it wrong, right? It's going to get it wrong. This is not a person, that's just a machine. So the goal here is to reduce the error, to make the error as small as possible. Now, data scientists, because again, they love to use words that nobody understands, they talk about loss reduction here. Actually, it's the error reduction. And how do they do that? Well, imagine that you have 2 inputs. And then you have 2 weights, W1 and W2, okay? Just 2 inputs. And you say, you know the answer to the output that you want to find out. You know the mathematical answer. And you know that when W1 and W2 are around here, you have a big error. This is very wrong. You don't want to go there. When you are here, you have a very small error. So this is good. This is a good value of W1 and W2. But you also have sometimes what they call some local minimum. For example, here, you see this is not the smallest value of the error, but it is smaller than around it. So what we call here, we call that a loss landscape, all right? And don't forget that here we have only two inputs, all right? 2 weights. So this loss landscape, we can actually represent it in 3 dimensions. But of course, when you have X or when you have N inputs, it's impossible to represent, but there is still a loss landscape that computers can actually use. So how are we going to try to find out with trial and error where is the lowest possible error? Well, what we're going to do, we are going to say, all right, I'm going to take a random point, and then I'm going to use a derivative function that we talked about before to calculate the slope at this given point. And so here is the slope. This is not the steepest slope ever. The steepest slope is going to be here. So what it means is that I check where is it the steepest, and then I'm going to take one step in the opposite direction. And the value of this step depends a little bit if you know your system very well. So if you have a system that you think the loss landscape is rather smooth, you can probably take a big step. So it's going to be faster to compute. On the other hand, if you don't know your system very well, you're going to take a small step because you want to be careful that you don't have maybe a minimum at some point or a local maximum, which is going to throw you off. So you take a step, and then you're going to do the same thing again. You're going to calculate the derivative of this function at this location. So you have the slope, and then you're going to take another step. And ideally, you're going to do that, and you're going to end up in the global minimum here. But there is a risk because you have some local minimums. So maybe you take a wrong turn, and then you end up stuck here, okay? So to avoid doing that, we are going to try with another random point, and then we do a descent. And we try another random point, and then we do a descent. And when we do that, we talk about epochs. Every time that we calculate one descent, it's one epoch. And then you can do that multiple times. Landscape like that, loss landscapes can be extremely complex. All right, so here is an actual concrete example where you see that you have a lot of local minimums and you have one clear global minimum, which is where you want to end up. But of course, to end up in this global minimum, you need to try many, many times. Okay, and here again, when we try one time, we talk about one epoch. When we try twice, two epochs, three times, three epochs, etc. So in practice, how does this work? Well, in practice, the computer is going to do that. They are going to start with a random point and descend, start with another random point and descend. This is called gradient descent. You descend along the steepest gradient. That is very expensive to compute because every time they need to calculate the slope. And can you imagine the slope when you have a system with, 300 inputs or 5,000 inputs? This is extremely complicated to calculate. Thankfully, they can do some of this computation using the GPU, so it's a little bit faster, but still you need some very, very beefy computers to do that, okay? So don't try this at home. That's kind of what I'm saying here, unless you have really a very good computer with a good graphic card. This is going to take a long time. The fact that they select a random point and they descend like that, it's called stochastic descent. This is another one of those words that nobody knows what it means. Actually, stochastic means, and thank you Wikipedia here, it means random, something like that. So this is a random descent, if you want. So let's talk about a concrete example. I mentioned already my good friend Cesc Juarez. He's amazing. He's a data scientist. He's a developer. He understands those things very well. And he came up with a model which is going to help me understand if the picture is a hot dog or a pizza. Funny story, I showed this presentation in Italy once, and they told me, oh, neither one of those pictures is a pizza. That doesn't look like a pizza at all. So bear with me. We are going to say, for the sake of the experiment, that the top picture is actually a pizza. All right. We are going to see in this small video that I'm going to show you, which has been shot by Cesc, a few tools. So we are going to see Python. Python, why do data scientists often use Python for artificial intelligence and for model training, etc.? It's because Python has huge numbers of libraries, and they have also in the language some built-in features. For example, the dot product. Remember when you have vectors and you want to multiply them together? This is just built into Python in some libraries, etc. So you can use those libraries to write less code and get the same result at the end. Then we are going to use PyTorch, which is basically a framework that is going to allow me to train a model. And you can parameter the way that you train it. An alternative to that could be TensorFlow. There are different school of thoughts about which one is best. Here we are going to use PyTorch for that. Now, Cesc is also going to use Jupyter notebooks. So Jupyter, notice a PY, okay? That has something to do with Python. It's going to allow you to run Python code in your web browser. And the cool thing with Jupyter notebooks is that, first of all, it allows you to experiment with your code very easily. You can just go and modify your code locally, tweak it, and then run again, and it goes very fast. You don't even need to build anything. It's just going to run in the web browser. Also, you can connect Jupyter notebooks with Azure, and we'll see how he does that in the demo. But basically, you can say, all right, now I'm going to train my model locally, with maybe just one epoch to go faster. And then when I'm happy with the result with my code, I'm going to publish all that to Azure Machine Learning, and then I'm going to run that multiple times, much faster, until I have an actual model. Visual Studio Code, we are going to use that to tweak the Python code. All right, there is a Python extension. I'm giving you the link at the end, which is going to help you with things like syntax highlighting and also auto-completion, etc. Azure Machine Learning, because we need some very beefy computers to run this code. And so we are going to do that on clusters of computers that we don't want to buy because they are very expensive. So we rent them from Azure. All right. And then Azure Container Instances, because once you have the final model, it's going to be deployed as a container. And then you can run it, for example, in Azure Container Instances or in Docker or in other container systems where you can expose an endpoint. And then that's going to be basically an API, a REST API that you call with a picture. And then it's going to tell you this is a pizza or this is a hot dog. All right. So let's see this demo. So this is a small video. I'm going to go through it and I'm going to pause from time to time to explain what's going on. So first of all, Seth is going to start Jupyter Notebooks. And here you see he's in his web browser. And here he has some code that actually he told me very openly that he took from the internet. So data scientists work just like us, just like us developers. They go to internet. It's not Stack Overflow. It's maybe something else. But basically, they go there and then they find something that works and then they take it and tweak it. Okay, that's kind of the idea. So here you see the different cells of the model. Here you see something which is really cool is that there is a function which is called train model, which is going to be super convenient. Notice that we have something here which says number of epochs. Remember, epochs is one descent is one epoch and then another descent, etc. Here is going to try with 25 epochs. Why not 500 epochs? That would be even better, right? Well, it's a little bit like before. There is a certain number of trial where it doesn't make sense to do more because your result is good enough. And if you try again and again and again, the result is not going to change enough to justify the cost of trial. So here, 25 epochs is probably a good number. And this code is going to train. I'm not going into all the detail of this, but essentially what he's going to do, he's going to take a set of known data. He's going to give that to the model. The model is going to calculate the W's and the B's until it is satisfied with the error, with the loss, which has to be as low as possible, as close to zero as possible. And with the accuracy, we know the accuracy because we have labeled the data, so we can compare the result of the computer to the actual data. And you want the result, the accuracy to go as high as possible, as close to 100% as possible. And basically he's going to run a number of epochs until he finds those W's and those B's, okay? Cool. So here, Seth took the same code that you had in the Jupyter Notebook and put it in Python to basically modify it and have a little bit more convenience here. And then what we are going to do is that we are going to run the code here in Python. And we are going to see here the result. So you see that after running, he had 883 training pictures. And then he had a set of pictures that he kept for validation of 20 pictures. We'll talk about that in a second and understand why the validation is important. So now the computer is going through, okay? You see the value of the loss. We want the loss to tend to zero. That's kind of the goal that we have. And after running one epoch, we see that we have an accuracy of 73%. It's not very high. And we have a loss of 0.59. As a reminder, we want to go as close to zero as possible. So here the loss is pretty high. So the training for one epoch is not great. But on the other hand, when we run it on the validation pictures, those 20 pictures that we reserved to check the result, it's actually not too bad. It's 0.1 loss and 0.95 accuracy. But I'm sure we can do better, okay? So how can we do better? Well, basically what we are going to do, first of all, let me show you that this Python code is also saving the model. This is the actual model in ONNX format. ONNX is a standard format that is used a lot in computing. There are other formats that you can use for models like that. There is also a visualizer for those ONNX models that you can open here. And here you see those are all the layers of our model, okay? And from time to time, you see some things like, you see here, there is a ReLU. there is an activation function, and there are a lot of ReLUs in these models. There are a lot of different activation functions. Here there is a reshape. This is another type of activation function. And here you have, if you open that, you see the value of those B's, and then at some point you will have the W's as well, so the weights and the bias, which have been found by the computer by trying and getting to the lowest possible error. All right, so that's the model that we have. Now again, this is a model that was created after one epoch, so it's not great. So now let's go to another Jupyter notebook, and here what we are going to do, we are going to take the exact same thing, but we are going to run it on Azure, and we are going to increase the number of epochs to 25. Like this, we are going to see that it's going to go faster. For the pictures, we save them as blobs in blob containers. This is apparently a hot dog by American standard, I believe. I wouldn't necessarily eat that, but whatever. And then here, the code is going to be run. The model is going to be saved. So first, let's run the code on Azure. So by the way, I speed the time. You see, this is the time here. So I speed it up quite a bit because a lot of it is waiting on the cluster to be actually free on Azure. And then it's running the code, which is going to take some time. You see that here we have the accuracy that is tending to 1 and the epoch, which is tending to 0. And the computer at some point is going to say, all right, I ran my 25 epochs. I found the best possible value of W's and of B's. And basically, that's the model that I'm proposing to you. Everything is saved on Azure in those notebooks. All right, so this is convenient because you can go and find it out here. And then the next step is going to be saving the model. The model is going then to be exported into a container, into just like a Docker container if you want. And then we are going to deploy that to Azure container instances so that it can be run as an API. And in just a second, we are going to get here the value for the API, the URL of the API. So then we can test that. Let's go and select random pictures of pizzas from the internet. This is the endpoint. This is the URL of the image. This is a pizza. Okay, that works. Let's look for a random hot dog. Same thing. We copy the URL. We check it out. We send that to the API, and then we see that we have a hot dog. So it works. The result is what we were expecting, and this is in essence how data scientists train actual model. Now this one was relatively easy because we just had two classes that we wanted to reach. You can imagine that when you have a lot of classes, it gets all much more complicated, obviously. All right, so let's talk a little bit about some issues that we want to solve. One issue is called overfitting. What is overfitting? Well, if you have here, a curve, rather some points that were measured in a system, and you decide to run a straight line through it, it's underfit. It's not great. You have a lot of error. Here you have a big error. Here you have a big negative error. So basically, you can do better, and probably a better result could be a curve like that. Okay, this is pretty fit. It's a simple curve, so it's easy to calculate. It's not going to take a lot of computing power, but at the same time, it's quite close from all the points on this system. But computers are overachievers, and they love to reduce the error as much as possible. And maybe a computer is going to find a curve which is like that, which goes through every point, and it's overfit. Why is it overfit? Well, first of all, it's going to take a long time to compute values for this curve because it's a very complicated function. But also, this curve is perfect for the measured numbers. But as soon as you add another number from an actual system, maybe it's going to be outside of the curve, and then you're going to have some errors again, right? So it's not worth doing that. So definitely this one was fit, it's good enough. This one is not great. It's perfect for the measured system, but it's not great for the actual system, all right? So you want to avoid that. How do you avoid that? There are different techniques. One technique is what we call regularization, which is basically you're going to, every time you run an epoch, an iteration, you're going to use only 50% of the neuron, randomly selected. And then you're going to run another 50% and then another 50%. So basically you make the computer a little bit dumber than it was before. And you hope that it's going to create a situation where it's not being as perfect as possible. The other case, which is probably more used, is early stopping. And this is where we use the validation data. Remember, Seth had selected 20 images for validation. So basically what we are going to do here, we are going to say, all right, I have the error, and then I have the number of iteration, and it's probably going to go like that. The error is going to go smaller and smaller as I increase the number of iterations, the number of epochs, right? But this is for the system we know. And then if we take a system we don't know, if we take those 20 pictures that have not participated in a training, maybe it's going to go like that. And at some point, it's going to start diverging. You see here, it's diverging, right? So the perfect value is around here. And this is where we are going to stop the iterations. That's why we went to 25 epochs and not with 500 or 1,000 epochs. First of all, it would take much longer to calculate. Second of all, it would probably at some point diverge because the computer is going to go too close from the known system and it's going to ignore the unknown. All right, so that's a good thing. Now, of course, there are other things when we talk about artificial intelligence, which are more, I would say, more worrying for the public, right? They are not technical issues. Things like bias and things like misunderstanding the data. So there was an experiment done a few years ago where people, doctors thought, hey, maybe we can take the history of our patients, teach a computer to create a model based on that, and then we are going to be able to detect if a patient is prone to have pneumonia in the future based on his medical history. But the problem is that the computer came up with something which was very weird. The computer said if the patient has asthma, the probability that they are going to get pneumonia is very low. And that was based on the training data. And of course, it doesn't make sense. When you're a human and you think about it, you realize that if somebody has asthma, they already have an affection of the respiratory system. The probability that they are actually going to get another affection, which is pneumonia, is rather high. So how is that even possible? Well, actually, it's not really possible. This is a problem. And the human doctor found out that there was a problem here. And they said, well, yeah, it's because if you have asthma, you're very attentive to the way that you breathe. And if you have difficulty breathing, you will go to the doctor much earlier than people who don't have asthma. So if you want, the end result is the same. Asthma patients had less pneumonia than non-asthma patients. But the reason was not because of the asthma, it was because they went to the doctor earlier. And the doctor was able to treat that, and it was not, going into a state of pneumonia. So, of course, you can go and fix it in the data and say, oh, okay, we need to ignore asthma patients. But then what else did we miss in the system? And eventually, the people who were developing that system were uncertain and decided not to use the model. So this is something where you need to always question the whole model. It's very important when you do AI, you need to question your data. You need to question the results. You need to analyze the results all the time. Okay, because sometimes the computer is going to misunderstand the data. Now, of course, another problem is things like racial bias. This is really bad. And this is very often based or due to bias in the data. If you collect data out of a white-only population, and then you run some images of people of color in the model that was created with this data, the model doesn't know that there are people of colors because he was only trained with with pictures of white people. Okay, this is what we call racial bias. And here we see something which was terrible, is that at some point Google Photo was misclassifying people as apes, which is of course terrible. They promised they fixed the problem. They actually didn't really fix the problem. I think the way they fixed the problem is that they stopped recognizing gorillas. But basically, this is a symptom of not having enough diversity in AI, in data science, in software programming. Because if you have only white people training the models, they are going to forget that there are other people than white people. Okay, and same thing for gender bias, same thing for other type of bias. So those are all problems. Unfortunately, it's a little bit out of the scope of this presentation, but I want to make you aware of some resources we have. So here at Microsoft, we have something called FATE, Fairness, Accountability, Transparency, and Ethics in AI. Very interesting webinars. if your firm uses AI, you should probably do those webinars, and everybody do those. Not just the scientists, the data scientists who are developing the model, but the CEO, even potentially the cleaning lady, because maybe they will detect some problems that you wouldn't think about otherwise. Okay. I have a whole talk about ethics in AI at this URL. So please feel free to check it out. It's on YouTube and it's about an hour long where I go quite deep into those problems. Okay. All right, I want to mention that if you're starting with AI, a good place to start, especially if you're a developer, is our cognitive services on Azure. We have a lot of those models which are pre-trained, pre-packed in the domains of vision, speech, language, knowledge, and search. And then we have some APIs, REST APIs that you can use to go and to try this out, or some SDKs if you prefer that in .NET, JavaScript, Java, and much more. It's really cool place to try using AI without having to actually train the models by yourself. Finally, here are some resources. So first of all, if you want the slides, if you go to gslb.ch/philug 2022 or this QR code here, this is where you will get the slides as well as a link to the video by Seth. So you can go a little bit slower through the video to understand. Then we have the MIT course that I mentioned before, which is basically where I went through and learned some of this stuff. We have also some Learn modules on Microsoft.com/learn, which are talking about machine learning and specifically Azure ML. Jupyter Notebooks and Azure, there is some documentation about it. And the extension for Python for VS Code that I was mentioning before, which is doing things like syntax highlighting, auto-completion, etc. You can download it there. Additional information about PyTorch, TensorFlow, Azure Machine Learning, Azure Container Instances for Azure for machine learning. So everything you need is at this URL, so gslb.ch/philug 2022. And finally, if you want to talk to me, feel free to contact me on Twitter. I'm L Bugnion, or this is my email address at Microsoft. Always happy to talk to people, especially my dear Filipino people. Believe me, I can't wait to come back to the Philippines. And this time we'll go in person, I promise, at least if the situation allows us. Thank you so much for listening. I hope it was useful for you. I didn't see tons of questions on the chat. I saw a few interesting comments, so feel free to check the comments. I saw some people definitely know what they are talking about and posted something, so really good. The Silicon Valley hot dog versus not hot dog. I think this was clearly Seth's inspiration when he developed this thing. And definitely a great episode as well. So thank you so much.
Yeah, thank you, Laurent. So I'd like to ask the audience if they have any questions, please feel free to put it in the chat. But I do have one question of my own. Oh wait, before we go to that question, I had an interesting question from my friend Paolo. His name doesn't appear in the chat, but just I guess out of curiosity, does ML.net use the AI course? I think it's not AI course, right? The Apple M1 chip has some sort of neural engine technology. I don't know how that works, but just out of the
this
blue,
is exactly one of those cases where I'm not sure about the answer. That said, if our good friend Facebook user here wants to send me an email, and I can try to ask the .NET people for sure if they know the answer. I personally don't know the answer, I have to say.
Okay.
I can imagine that there is some level of optimization done in ML.NET, but I wouldn't know that. My gut feeling is that they don't. That would be my gut feeling.
Yeah.
.NET being basically an abstraction, right?
That's true. That's true. And it would be it wouldn't be optimized towards one processor. It would be optimized towards of a variety of processors.
Potentially, but maybe they do some magic, in the just-in-time phase of the .NET compilation. I don't know. My gut feeling tells me that they probably don't optimize for that particular processor. But everybody always comes with additional optimizations and all that. That's of course a difficulty for languages which are relatively abstracted like .NET or Java, for example, to adapt to each one of those. And I know for a fact that they do some optimization based on the type of processor. So yeah, maybe someday. My guess is that at this time they probably don't. Yeah.
Yeah,
I see an
that's
interesting comment also. Greg Cyrus here in the chat says, as human, one could detect the error by racial bias, which is probably true, but keep in mind that when you detect the racial bias, often it's too late. Often the system is already in production. And we had some cases like that where if you live in the US, you probably have seen that when you go into a plane right now, you are identified by an AI system, basically. So at the gate, you don't show your passport anymore, you show your face, and then it scans you and recognizes you. And this is all good, but unfortunately, some people of color had the problem that they were just not detected by the system. And this is typically an issue where I don't want to assume, but I'm pretty certain that the system was developed by white people who just didn't train the system with people of colors, and the system just didn't see the person of color, which is terrible when you think about it, because imagine that it means that you cannot go into the plane because the system ignores you, right? So this is bad. So yeah, we can detect the error. Ideally, we'd like to detect the error during the not during the production phase.
Yeah, during some sort of testing.
And this is why diversity is super important in this system, as well as really going out of your way to test with edge cases that you didn't think could happen. It can have some repercussions, some terrible repercussion where you hurt people terribly, not just their feelings, but basically you hurt them physically, right? In certain cases. Yes. Imagine that you have a door which suddenly closes because it thinks there is nobody in the gate, and actually there is somebody and the person is stuck, right? These kind of things, right? So it can have some physical repercussion, which are of course terrible. So again, I really encourage people, if you go to the slide deck and find my talk about ethics in AI, I have a lot more there. Here I decided to dedicate approximately 10 minutes of the presentation to that because this is super important. But the other talk is almost an hour long, so definitely more information there.
All right. Thank you. Yeah, definitely, it's a big issue, and it's not just. I don't think it's just skin color. It's
gender. It can be.
It can be gender. It can be clothing. For example, the traditional clothing of people from South Asia, the Middle East, can mess up with the recognition algorithm. So
completely.
If it's
there are all kinds of biases that can happen, and each of those biases can be very harmful. So we need to think about it during the development phase. Yeah,
that's true. That's true. All right. I want to go back a bit to the discussion we were having about the processor optimizations, because there was one thing that caught my eye in Seth's code, which was it was trying to recognize if you had if it was between a CUDA and CPU. CUDA is I think that's the protocol used by GPUs. I am aware of NVIDIA CUDA. It was in the very first part of that video that you showed. So one thing I'm curious about is first thing I'm curious about is, does Azure ML, for example, does that try do they what do you call this? Do they have GPUs for these kinds of processes?
Yeah. We have tremendous machines which are extremely expensive, and so that's why, John, you and I probably. I mean, I know that the first time I sat in front of a computer, it was not actually a computer; it was a terminal. And then we had the mainframe in my engineering school, and basically we were coding. We were essentially renting time from the machine, right?
That tells our age.
No, absolutely. But this is interesting to see that now we are a little bit back to that, right? With the cloud model, with hybrid models where we run code on our local machine, but we also run a lot of code on other machines, right? Things like GitHub Actions, for example, where we run code on GitHub server. or of course everything that happens on Azure with Azure functions and app services and everything, where we don't want to have our own machines running that code. And ML is a great example of that, because those machines are so expensive that you can't afford to buy them. And in fact, it wouldn't make sense to buy them. Exactly, we're back in that era, because it wouldn't make sense to buy them because you're not going to use them enough that it makes financial sense to buy them, except in a few specific cases. It makes much more sense to go and rent those machines from somebody else. And in the case of Azure, we have machines with very, very big GPU, quantities of GPU with tons of RAMs. I forget the exact the maximum value we can have, with also a lot of nodes, like a lot of cores, etc. And those machines being very expensive, it makes sense to use them as in an optimized manner, where you're going to say, all right, I'm going to push that to a cluster. You saw that in the video, there was a little waiting time in the beginning. Essentially, what it was doing, it was waiting for a cluster to be free so that it could run the code on it. The cool thing is that before, when you wanted to have when you wanted to rent a mainframe like that, you had to say from what time to what time. And now you don't need to do that anymore. You can push it and say, well, okay, I'm just going to wait until the next one is free. This is all optimized. That said, you also have possibilities to say when you want to run your code, because there are some times which are maybe less busy and this is going to be less expensive, etc. But this is all optimized, and that allows you really to run things that we couldn't do before. It's not just the CPU and the GPU and the RAM and everything, but even just the data storage, right? Storing data in Azure makes more sense because, first of all, it's going to be optimized. It's going to allow you to run some, for example, when you want to avoid bias in your data, you want to clean your data. This is super important. So you're going to collect data, you're going to clean it. Those cleaning algorithms can be run on Azure when you ingest the data directly. And that's going to be very convenient, because you don't need to do that on your own machine. You can do that when you ingest, which allows you also to ingest data automatically. You can always refine your data by ingesting the data automatically and basically cleaning your data, for example, by eliminating extreme values or things that don't make sense, these kind of things. And then also, because when you have the data in Azure and your clusters in Azure as well, we have some very high-speed lines between both. You can mount, for example, the blob containers that Seth was using in the demo with the pictures. He was mounting them, so there is no download. It's just mounted as a drive, and then basically the cluster can access the data as if it was a local drive with very fast connections. So all this is optimized, and it definitely makes sense to use that, unless, of course, you have a very good reason. Think about, of course, if you want to keep the data on national soil. Unfortunately, we don't have data centers in the Philippines at the moment, for example. So there is this aspect that you need to consider, right?
All right. Yeah, absolutely. And of course, we also have to consider the actual cost of running those algorithms here. I mean, on Azure. I wouldn't think that they're too much, but no, it still have to watch out for it, I suppose.
Yeah, absolutely.
All right, cool. I do not think we have more questions. Any parting words for us before we go?
Well, I mean, it's a very interesting phase that we have right now with all this online learning. I'm very happy that I had the chance to reach out to people there and talk to you about this. Nonetheless, pay attention to a few things we have going on. We have Build coming up very soon, end of May, 24th to 26th of May. And this is going to be interesting to see what Microsoft is working on with our latest content, for sure. And also, I'm going to pimp my own thing, which is Learn Live. I'm running a show called Learn Live on different platforms. And if you just go to ak.ms/Learn Live, you will see our program and what we have going on right now. Nothing right now about machine learning, I'm afraid, but maybe in the future. But we have a very diverse set of aka.ms. Sorry, you need to
AK. All right.
like as known as
Okay.
Yeah. So that's the short link exactly. So if you go there, you will see our program. This is a series a series of series really that I've been producing since November, and we have some good content here. So we'd love to see more of you there. And of course, next time I'm in the Philippines, definitely we are going to try to organize something, and we'll have some lechon or something, right?
Yeah, absolutely. More lechon, the better. And
All right.
yeah, again, just to emphasize that all of the material that Lawrence showed us is available in this link of gslb.ch/
Hmm.
PhilUG 22. So with that, I'm going to let you go. I'm conscious you have something up 30 minutes from now or something. So
Indeed.
yeah, thank you so much, Lauren, and yeah, we hope we look forward to that hybrid event
Yeah.
that we'll probably do later this year.
Me
So
too very much. Yeah.
yeah, I'll see you then again. All right.
Okay. Thanks for
Thank
having me,
you.
John,
Thank
and take
you.
good care of you all. Bye bye.
Yeah, bye bye. All right. So that is our event for tonight. So please continue watching our meetup.com and our Facebook group for new events, and follow our Twitter as well. We will announce events there. And yeah, thank you very much for joining us in this really wonderful discussion this evening. It was a gentle introduction. It was a bit not so gentle on the math, but enjoyed it nonetheless. So I enjoyed it. I hope you enjoyed it too. So with that, thank you very much. I am John Limha. Magandang gabi sa inyong lahat. Good night and see you next month. All right. Bye bye.